Hey everybody, we're here at 5.3, lipids. Lipids are things like fats, oils, waxes. They can be used for insulation, like if you can think about polar bear putting on fat before winter. Energy storage, there's a ton of energy in there. I'll point that out to you. Also, I know that we have some fat that covers our organs, like say our heart, for cushioning if you have an impact. Lipids are used to like coat things like leaves so that they're waterproof. They coat fur and feathers and things like that. So think about lipids and enjoy. I hope there's a lot to learn here. Follow along in the textbook, please, if you can. Before we go any further, I want to take a pause, and I want you. So it's easy in biology, especially in the first month or two, to get like so focused on the minutia and all these atoms and bonds and all this crazy stuff that's so small. This is not biology. It's components of things that are alive, but these things aren't alive. And so let's just refresh ourselves with the big picture.
I see trees of green, red roses too. I see them bloom for me and you. And I think to myself, what a wonderful world. I see skies of blue, clouds of white, bright, blessed days, dark, sacred night. And I think to myself, what a wonderful world. The colours of a rainbow, so pretty in the sky. Also the faces of people going by. I see friends shaking hands, saying, how do you do? They're really saying, I love you. I hear babies cry. I watch them grow. They'll learn much more than I will ever know. And I think to myself, what a wonderful world.
Okay, I'm sorry. Bless David Attenborough. He is one of the kings. Him and a few other scientists are the kings of biology. I have a biology degree, a bachelor's degree. I was studying biological sciences for my PhD, which I never finished. But the point is I know a lot of biology. I've taught this class for 20 years, now 20 years plus. And I'm going to tell you, the lions are not laying down with the lambs here. When I think of biology, I think of three things: reproduction, misery, death. That's what I think of it. And I hate to say it, evolution is my favorite unit. So, I mean, that was a nice break, wasn't it? All the music that was put. Anyway, let's talk about lipids here. I'm going to read this. It says lipids are a diverse group of hydrophobic molecules and are not macromolecules. The idea is that all of these things, you can put together these monomers to make polymers. They become macromolecules. Lipids are different than proteins, nucleic acids, and carbohydrates. And I'll show you why in a second. Also, they are generally non-polar and they are hydrophobic as a result, meaning they don't dissolve in water. You've seen people pour oil on top of water before and it doesn't mix. I've done that for you. The general kind of structure of most fats is the triglyceride, meaning three. These are glycerides here attached to a glycerol, or fatty acids attached to glycerol. Triglycerides, fats or oils, are an important energy source. You can see that right there. You can also see phospholipids. You've probably heard of those before. They exist in cell membranes. We have a bilayer of them. Where do you think you get all the fatty acids to make the fats that are in your body, the appropriate fats from in your body, and the appropriate phospholipids? You get them from your diet. And so if there's one thing I want you to gain from this, besides all this minutia here in detail, is you are what you eat. And so if you eat good fats, you're going to have good fats that build these things in your body, and you're going to be generally healthier than people who eat bad fats. And I'll make the distinction between the two types of fats in just a moment. Here's some lipid bilayers. We see steroids here. We'll get to that in a few minutes, way over here on the other board. 4 fuse rings attached with some chemical groups. You've seen cholesterol. We saw the 2 sex hormones in chapter 4, estrogen and testosterone. Well, we mentioned this. Don't form polymers. This is a standalone entity here. We're not going to make thousands of these together through dehydration reactions to make this long superfat. They just stand alone, essentially. Also, because they have primarily hydrocarbons, which you can see, of course, they have some oxygens at one end, but I would say 90% plus of the molecule is just made up of carbons and hydrogens, non-polar bonds, covalently bound, sharing electrons equally. Therefore, they don't have kind of these dipoles or partially positive and negative sides to the H's and the C's, and they just don't dissolve well in water because of that. They can't form hydrogen bonds there. Well, make sure that you understand this. This is a picture from your textbook. Here's the dehydration reaction in the making of something called a triglyceride, which is a type of fat. You can see here that a hydrogen atom is coming together with a hydroxyl group, and we're going to put 3 fatty acids on here. This is called a glycerol way over there on the left side, and then there's a fatty acid right there. We've got, it's called an ester linkage. I would memorize that. That's just this O-C double bond O linkage. See here that there's 3 fatty acids found. They're usually about 16 to 18 carbons long, but of course, if you go to the islands around the equator of the world, there's oils that exist in some plants that are longer, in some of these nuts and stuff, and you can get these weird long types of fatty acids. Rapeseed oil has like 26 carbons or something like that. There's just a lot of different variations there. And I would say it's good to eat a varied diet so that you have different fatty acid lengths on the triglycerides that you make from the food, the fats that you bring in. And fat's good for you. People have been telling you for a long time, olive oil and avocados are good for you. Those are good fats, and I'll show you why in just a second. This is a triglyceride that we have here. Well, I have up here 2 types of fats on the board, saturated and unsaturated fats. Here's an example of a saturated fat. I want you to write down a few things. I want you to write down animal, flat, and I would say bad. So you can say it stacks flat. I'll show you why in just a second. But this is generally the fat that comes in animal products. These are normally solids at room temperature. So I have this stick of butter. Full disclosure, I just did get this out of the refrigerator. However, if we were to leave this out on the countertop for 6 hours, it would not turn into a pool of oil. It would still maintain, be gross and flimsy, but it would maintain its shape a little bit anyway. Let me put it back in the bag here. The idea is that the reason why it is so stable at room temperature and is still a solid is because of its structure. So I'm going to put some C's on here, and the idea is that this is called saturated, which means at every carbon it has a full saturation, or as many hydrogens as possible. And I welcome you to draw this, please. Press pause if you need to. This guy down here is going to have 3 hydrogens. Well, if you can imagine around the outsides of these hydrogen atoms, there's these electron clouds, and these are negatively, I'm just putting a negatively charged electron. That's supposed to be an arrow there. The thing's supposed to be swirling around here. But this guy also has one. And these like charges repel one another. So you can imagine that these are pushing away from each other, and conversely, these are pushing away from each other here. I'm just drawing an arrow going two ways here. The idea is that this gets super rigid, and that's why this stays flat. And that's why then fats can stack on top of each other. And this is why it's solid at room temperatures, because it's super stacked and flat. It's tough for us to break this down. We can get it in our body. It's natural. So we're used to breaking it down. But if you get a lot of it, often it gets out into the bloodstream before you can break it down in your digestive system, because it is so tightly packed there. This is saturated fat. They have the maximum number of hydrogen atoms possible and no double bonds. That's kind of the definition. Write that down. A diet rich in saturated fats may contribute to cardiovascular disease through these deposits of plaque that settle down in the arteries. You probably have them in every artery, but the most important arteries to keep clear are the arteries which feed blood to the heart tissue muscle, so that these muscles can do cellular respiration, make ATP, and then contract. And so what happens is people have heart disease, which is the #1 adult onset disease in our country, and it's often caused by poor diets. And one thing that really contributes to it is the clogging of these arteries with this saturated fat. There's also a touch of cholesterol that will do it. But the point is that there's less blood going through because it literally has plaque. You know that the person who cleans your teeth at the dentist, they scrape off plaque. It's just like gunk on an engine of a car or on your teeth. It just deposits in there. Often people will have to get heart bypass surgery, which just means from the aorta, which has this nicely oxygenated blood on the left side of the heart, which has come from the lungs. The idea is that you literally are bypassing these arteries because they're so filled with fat, or sorry, of this saturated fat, that you actually have tubes that then go into fake tubes from science that go into the heart tissue muscle. And so you can feed the muscle blood that way, essentially. Well, there's another type of fat. I'm going to move this over here. Called unsaturated fat. What do you think are some characteristics of unsaturated fat? Well, I'm going to write down here plant. Just write kinked, which what I mean is that it has some shape to it. It's not flat, and you can see the picture here is that it has a kink to it. And I'm going to write good, and then you can write a liquid at room temperature. I just written up here liquid at RT. Example of an unsaturated fat would be like this. It would be canola oil. You can imagine that this would be a lot cheaper to make than a saturated fat. Think about growing up, say, a pig or a cow and then harvesting the animal and getting the fat out of it, or I guess milking a goat or a cow and getting that fat and making butter. It's much easier to just have a bunch of plants and then press them down in some sort of press, and they get the oils from the plants. So this is unsaturated fat. If you notice, it's a liquid at room temperature. And the reason why is because of its structure. So what it means by unsaturated is that it has not a hydrogen atom at every available spot, in theory, on every carbon. So let me show you what I'm talking about. So you can imagine at this carbon here, we have 2 hydrogens. Same with this one. But when we get over here, we get a double bond. The idea is that instead of having 2 hydrogens, we only have 1 hydrogen here and here. And in this case, this is a trans fat. You can see that the R, or the rest of the molecule, isn't on the same side, but it's on opposite sides of this double bond. So this is a trans fatty acid, or trans fat. And what then happens is that they can't pack down and line up on top of one another, so they kind of just fall all over each other, and then they become liquid at room temperature. So here's the structural formula of an unsaturated fat molecule. If 1 or more double bonds, you could get polyunsaturated fats, and those actually will have more than 1 kink. Lots of cold water fish. What's interesting is that these cold water fish, like flounder and stuff up near Iceland and Greenland, super cold Arctic waters, they don't have animal fats. They actually have unsaturated fats. I'm not going to say that they have plant fats, but they have a type of unsaturated fat. And the idea is that if they had saturated fats, they would be literally frozen solid. They're structures. But as a result of having plant fats, then they can be a little bit more pliable and mobile in this super cold water up there. And so that's why people take fish oil pills, where they say, oh, eat fish, it's good for you. You can get these fats. Also, lots of hot weather seeds and seed coverings, like a coconut or maybe an avocado. These things are going to have often very unsaturated, multiple polyunsaturated fats, so that they can be liquids at this super hot temperature down in the tropics. And so those, actually it's the opposite, sorry. They often have saturated fat. That's why coconut milk tastes so good, is because it is so hot. So they need a little bit more stability, so that not to be all runny on the inside. And so they actually have evolved to have saturated. Oh, you can see here, it's good for you. Go ahead and take a moment and distinguish between these two types of fat, please. But like I said earlier, it's a lot cheaper to harvest plant fats than it is animal fats. But there's a problem. So if I'm a food corporation and I'm making some Takis, aren't these fantastic? The problem is that you don't want someone to open this, stick their hand in here, and pull out a bunch of mush at room temperature, right? This is a liquid, right? So what happens often is that what food companies will do is they will partially hydrogenate a plant fat. And what they mean by that is they will actually add hydrogens here, and that will serve to straighten the fat. So you can pack it down more solidly, and then at room temperature you get more of a kind of a stable thing. And so you can look back here and see if there's partially hydrogenated oil. That's what that is. The problem with this stuff is that we haven't evolved to have enzymes that can recognize that and break it down. So what happens is often it goes out into your bloodstream and it will accumulate in your bloodstream, and that's a problem, because then it will pack in there just like the saturated fat in your arteries and serve to clog them. You know, I remember as a kid, we would go to McDonald's and we would get French fries, and McDonald's used to use saturated fat for butter for their French fries. It was like heaven, you know. And then the Food and Drug Administration said, oh my gosh, you're giving all these people coronary artery disease, they used to call it. And so they said, okay, just go to plant fats. But then they would dip the potatoes in plant fat and fry them, and they would be like, okay, it doesn't really taste that good, we can put salt on it. And so what everyone knew to do was go late in the day. So McDonald's, for instance, I'm not picking on McDonald's, fast food chains would take all this plant fat and they would heat it, put potatoes in there, and then they would cool it. And they would heat it and cool it, heat it and cool it. And over the course of the day, it would turn black. And what was happening was, with the bubbling and boiling of the oil, they were actually hydrogenating the double bonds and making it more delicious and more stable at room temperature. And anyway, it tastes better, but it's probably worse for you, for sure. So this is this process of adding hydrogen. But there's another thing the food companies do. They actually, if they say, okay, we don't use hydrogenation, we're just going to use trans fats. So trans fatty acids are found in fried foods, commercial baked goods, processed foods, and margarine. So if this is a cis configuration where everything's on one side, trans fats actually will move this thing. So I said it wrong earlier. So this was cis because this and this were on the same lower side of the double bond. But now if we bend this so now that everything is, oh, sorry. What they mean by the trans, sorry, I screwed this up, is that you can see there that on the double bond, they'll put the H's, you can see it on the screen, they'll put the H's opposite, and then that will serve to flatten it. That's just called trans fat. Sorry, I got all screwed up there. It's late in the day. The point is that This will also be a solid at room temperature. Problem is that we don't have enzymes to break it down. Our body cannot digest it. You can accumulate in your arteries, and you could have trouble feeding blood to your heart tissue as a result.
Trans fats, saturated fats, polyunsaturated monofood of what? People toss these words around all the time. Good fats and trans fats that you shouldn't be eating, but what are they really talking about? All right, so first we have to talk about what a fat actually is. Fats all have a pretty similar chemical structure of 3 fatty acid chains stuck onto a glycerol molecule to make a triglyceride. These fatty acid chains are long strands of carbon atoms arranged in a zigzag pattern. Now we have to step back just 1 second to carbon bonding. Carbon atoms each have the ability to make 4 chemical bonds. So in fatty acid chains, each carbon atom is using 1 bond to hold on to the carbon in front of it and 1 bond to hold on to the carbon behind it. In many fatty acid chains, all of the other available bonds will be filled with hydrogen atoms. In this case, the fatty acid chain is said to be saturated with hydrogens. A saturated fat. Now it's possible that 2 of those carbon atoms could double bond to each other. The formation of this double bond would mean that some of the hydrogens would disappear. Thus, the fat would now be an unsaturated fat. If there's only 1 double bond, it's called a monounsaturated fat. And if there are more, it is called a polyunsaturated fat. The carbon chain would additionally have to bend to accommodate this double bond. This means that instead of having a nice zigzag, you now have a kink in your fatty acid chain. Now, zigzag fatty acid chains are all the same shape, so they stack very well. This stacking creates things like solid fats, like a stick of butter. However, unsaturated kinked fatty acid chains don't stack very well, so they create things like liquid fats, like oil. So what about those trans fats? Well, trans fats are also unsaturated fats, but their kink goes in the opposite direction. This naming is based on the difference between cis and trans bonds. Cis means on the same side, whereas trans means on the opposite side. So while there is still a kink in this bond, the trans fats actually stack pretty well and can form solids. And they're not too easily broken down by your body. So, not so great. May your ingredient lists be a little less mystifying.
Olive oil is 100% fat. There's nothing else in it. Pancake mix, on the other hand, is only about 11% fat. And yet, olive oil is good for you. And pancake mix is not. Why is that? As it turns out, the amount of fat we eat doesn't impact our weight or our cholesterol or our risk of heart disease nearly as much as what kind of fat we eat. But let's back up. What is fat? If we were to zoom in on a salmon, which is a fatty fish, past the organs, past the tissues, into the cells, we would see that the stuff we call fat is actually made up of molecules called triglycerides, and they are not all alike. Here's one example. Those 3 carbons on the left, that's glycerol. And you can think of that as the backbone that holds the rest of the molecule together. The 3 long chains on the right are called fatty acids. And it's subtle differences in the structures of these chains that determine whether a fat is, let's say, solid or liquid, whether or not it goes rancid quickly, and most importantly, how good or how bad it is for you. Let's take a look at some of these differences. One is length. Fatty acids can be short or long. Another, more important difference is the type of bond between the carbon atoms. Some fatty acids have only single bonds. Others have both single and double bonds. Fatty acids with only single bonds are called saturated, and those with 1 or more double bonds are called unsaturated. Now, most unsaturated fats are good for you, while saturated fats are bad for you in excess. For saturated fat, the story pretty much ends there, but not for unsaturated fats. The double bonds in these molecules have kind of a weird property. They're rigid. So that means that there are 2 ways to arrange every double bond. The first is like this, where both hydrogens are on the same side and both carbons are on the same side. The second way is like this. Now the hydrogens and carbons are on opposite sides of the double bond. Now, even though both of these molecules are made up of exactly the same building blocks, they are 2 completely different substances, and they behave completely differently inside of us. The configuration on the left is called cis, which you've probably never heard of. The one on the right is called trans, and you probably have heard of trans fats before. They don't go rancid, they're more stable during deep frying, and they can change the texture of foods in ways that other fats just can't. They're also terrible for your health, by far worse than saturated fat, even though technically they're a type of unsaturated fat. Now, I know that seems crazy, but your body doesn't care what a molecule looks like on paper. All that matters is the 3D shape. where the molecule fits, where it doesn't, and what pathways it interferes with. So how do you know the food has trans fat in it? Well, the only sure way to know is if you see the words partially hydrogenated in the ingredients list. Don't let nutrition labels or advertising fool you. The FDA allows manufacturers to claim that their products contain, quote, 0 grams of trans fat, even if they actually have up to half a gram per serving. But there are no hard and fast rules about how small a serving will be, and that means you'll have to rely on seeing those key words, partially hydrogenated, because that's how trans fats are made, by partially hydrogenating unsaturated fats. So let's go back to our olive oil and pancake mix from before. Olive oil is 100% fat. Pancake mix is only 11% fat. But olive oil is mostly unsaturated fat, and it has no trans fat at all. On the other hand, more than half the fat in pancake mix is either saturated or trans fat. And so even though olive oil has 10 times as much fat as pancake mix, it's healthy for you, whereas pancake mix is not. Now, I'm not trying to pick on pancake mix. There are lots of foods with this type of fat profile. The point is this: it's not how much fat you eat, it's what kind of fat. And what makes a particular fat healthy or unhealthy is its shape.
Okay, honey bunches of oats. Anyone like honey bunches of oats? I want you to become a label reader. As I said earlier, I'm going to read to you what's here as far as lipids are concerned. It says total fat 2.5 grams, 4% of your recommended daily allowance. It also has a line for saturated fat, unsaturated fat, trans fat, and polyunsaturated fat. So now you know what these things are. Find them and become informed when you eat, please, if you didn't already know about this stuff. Well, there's just two quick things left: phospholipids and then steroids. Phospholipids are found in things like ATP and energy storage molecule. They're also found in the backbone of DNA. But we're going to be talking about phospholipids as they exist in cell membranes. You can see here that for every phospholipid, there is a polar and a non-polar end. In this picture, it says hydrophilic head. So there's tons of polarity there, meaning unequal sharing of electrons through covalent bonds. Water would dissolve that. Water would surround that and try to dissolve that portion of the phospholipid. And the bottom is going to be these long fatty acid hydrophobic tails. Remember, some scientists believe we make about 50,000 cells per second. So there's 250,000 cells that you just made, 250,000. The point is you're making cells all the time. You're getting rid of them, you're making them. And the question is, where do the the fatty acids and the phospholipids come from? They come from the food that you eat. So if you eat saturated fats, like you like to put manteca on your mom's coma. My mom had a coma, and we would fry things on there all the time. It was delicious. But the point is now I realize I can't eat that way because I'm making cells all the time, and I need to have these kinky fatty acid chains, because what you don't want is your phospholipids to pack too tightly, because I will tell you a major role of cells is to bring stuff in, materials, and then get rid of waste. And it needs a flexible, pliable membrane. Some scientists like to call it like a bag, aqueous environments, like a plastic bag, but it's moving and it's shaking and it's not rigid at all. And you want it to be that way. Of course, there has to be some rigidity to it so it doesn't disintegrate, but you don't want it to be too rigid or else it's tough to get stuff in and out. So here's an example of a phospholipid. Here's an example of a phospholipid bilayer here. If you recall how they kind of form themselves, they put their hydrophobic sides, or those heads, towards the water on the outside and inside of the cell membrane. And then the hydrophobic interiors are away from the water. Those are those fatty acids that are in the middle there. Well, the two fatty acid tails are hydrophobic, but the phosphate group and its attachments form a hydrophilic head.
Phospholipids contain a head group, choline in this case, that is attached via phosphate group to a 3-carbon glycerol backbone. 2 fatty acid tails are attached to the remaining 2 carbons of the glycerol. The head groups and the phosphate are polar, that is, they prefer to be in an aqueous environment. In contrast, the fatty acid tails are hydrophobic, that is, they are repelled from water. The fatty acid tails on phospholipids can be saturated with no double bonds, or unsaturated with one or more double bonds. The double bonds are usually in the cis configuration, which introduces sharp kinks. When forming a bilayer, unsaturated fatty acid tails pack loosely, which allows the bilayer to remain fluid. If there were no double bonds, bilayers would solidify to a consistency resembling bacon grease.
Okay, you can see here that when phospholipids are added to water, they self-assemble into this bilayer, putting the hydrophobic stuff inside, away from the water, and the hydrophilic stuff, the heads on the outside, and the inside of the cell, which is also an aqueous environment. You're going to see this as one of these potential essay prompts for the exam. Here it is. Go ahead and read it. Sorry, I thought it was on the next slide. Make sure that you get it down and make sure you can draw that for me, and I'll talk to you hopefully in person a little bit more about this. I want you to think of a cell membrane here, and I want you to think of stuff coming into the cell and stuff leaving the cell, and you want to have as kinky or as bendy of these phospholipid tails as possible, so this thing can be super pliable. This is a process called endocytosis. We'll learn about this in a couple chapters, and then there's exocytosis, getting rid of stuff, and just see that that membrane bends. So if you eat a ton of saturated fat, if you eat McDonald's all the time, or your cart as you go through the supermarket, you look down and it's all covered in plastic and with colors and everything all over it, you're probably getting a ton of saturated fat, and your phospholipids are going to pack really tightly. If you have lots of things that are more natural, you shop the perimeter of the store, you're going to have a lot more unsaturated fat, and you're going to have loose phospholipid packing. I once read that 10% of all tumors and cancers are caused by this inability for cells to get rid of their waste because the phospholipids are too tightly packed. So when it comes to fatty acid structure, making phospholipid bilayers in order for exchange of materials with the environment to occur, it's better to be kinky than straight. Don't forget that, please. I'm just kidding. Anyway, last thing, steroid. 4 fused rings. We know that sex hormones are types of steroids. There's cholesterol over here. They add stability to cell membranes. Some cholesterol we actually make, and some of it's good to have in our diet. It's good to have that. You don't want these membranes to be too flimsy. The way down here is the information on it. Cholesterol is here. I told you it's important. It's good that you have some. Of course, you want the right cholesterol, and I'll show you the difference between the two types of cholesterol right here. There's high-density lipoprotein cholesterol, which is more like I think of it as a snowplow or a scrubber. It is high density. It goes through our arteries, and it basically just scrubs them out. It scrubs out all the LDL cholesterol, which is kind of comes from animal products, and whereas the HDL comes from plant products. What you want, if you get a blood profile done, is you want a number. I don't know what the units are on here. I apologize for that. You want a number that's greater than 40 of HDL. Mine's always low. The doctor says, well, take niacin or vitamin B3, exercise, eat raisins, drink wine, all these things. I've tried to raise this. Resveratrol is this component that exists in grapes. And you can take it as a pill or whatever, and that's supposed to raise this number. I struggled to get my high-density lipoprotein number high to scrub out my arteries. I think it's genetic. The LDL level, you want it to be less than 100. You want this. It's like you want this magic ratio of like 5 to 1 here. You want the total cholesterol level to be under 200. But anyway, you just want to get your good cholesterol up. Just eat plant material and try to stay away from animal material as much as you can, because that will give you high levels of LDL cholesterol. Go ahead and pause for a moment. Press pause if you'd like. Go over all this stuff. Thanks.